your pen?
Nope.
No. Mine now. This is cool.
I'm gonna start seeing that.
Just a pen sleeve are gonna be glued
Oh
on.
my gosh, that's cool. That's a huge, huge element. So what is this, a practice talk? Like real practice or ideas talk or?
A combination of both.
Okay.
I've been a little more focused on finishing up a paper. And so I threw a bunch of stuff together so you'll get to kind of hear more layout and at least the way I'm thinking and see if it makes sense.
Gotcha.
How long do you think it will go?
Today,
Yes.
how long do you want it to go?
Well, we have room reserved until 6.
Mm-hmm.
So all the time is yours.
Okay.
But so just respect passions of the audience and give
Yeah.
some time for answers.
Okay.
So there are visitors, guests, and there are like native members of the group. So if you are visiting, just listen to John. If you are not just listening, well, everyone is welcome to do it next time, but for some of you it's optional and for some of you it's not, to bring your abstract for Sunnyville to the next meeting.
Oh, you guys are already doing that? Wow, that's early.
They do again in November now.
Oh, that's good to know.
Now we are disclosing important information to competitors. Okay, after it is disclosed, you may.
Well, it's if you want awards or anything.
So if you want to, you can also come here with your abstract and get a feedback.
Now that we know your competitors, you might not get very good feedback.
Are you going?
I don't know. I'm submitting an abstract, but I don't know where I'm gonna be.
John, can you start sharing your screen so that we see how it will go?
Yep. We'll just share entire screen. That's fine. You see a picture of yourselves?
Oh, it's really good.
Good. And now it is sharing. Okay. Yes.
Oh. Okay.
Very good. Because last time when we did a group meeting and you were presenting, I watched the recordings and slides were not flipped when you were flipping them.
Okay. Well, if for some reason it starts to lag a little bit, just let me know. Okay. So, like I had mentioned, I put a bunch of things together on the topics that I'll be talking about, and these aren't. Well, this isn't the final version by close, but I want to get your opinion on the layout of things, and if the most important points are clear and what makes sense and what you guys take away from it. And so this is going to be a presentation on the work that I've done over the last few years, primarily focusing on non-adiabatic dynamics, and that in and of itself is a very unique process, but we've applied this to looking at semiconductors, and more specifically quantum confined semiconductors, and how this is going to benefit society or the rest of us, or industry, wherever we end up. So just kind of what I'm going to cover a little bit today, a short introduction and motivation for why we're doing this, make it seem important to people who are listening, and then the methodology. So the way I have it broken up just a little bit in terms of what I introduce and where. And so that's something that you can comment on. And then we'll take a look at a little bit of work I did on silicon nanocrystals and looking at the influence of atomic motion on photoluminescence, line widths, and just the importance of atomic motion within studying materials. And then going forward, looking at the role of lead vacancy in perovskite materials. And so this is going to be the first step of looking at a bulk material, so we have something to contrast and compare to the work we did with the perovskite quantum dot in the next section of the talk. And then depending on where we're at for time, talk a little bit about polyoxide titanates. I threw a few slides in here, and there'll be more to come as well. Okay, so these are obviously things that, well, I guess for you guys, this isn't really that interesting because you just see white screens. Okay, so introduction. So why do we care about these materials? We're interested in these types of materials because, one, we know with growing population, energy demands rise, and obviously there's been a cultural shifting, moving away from fossil fuels towards renewable sources of energy. And so what types of methods are there, and how are these types of renewable energies harnessed? So one of the main examples is through solar panels, which is the picture on the screen, and primarily these are all built with silicon as the foundational material, but people are trying to find new materials, and that'll be some of what I'm talking about. Other opportunities to use these types of materials are in optoelectronics. You can see a number of diodes down on the bottom of the screen, ranging in various color. You can also see a number of vials with differing colors, all made of the same material, just having their color changed by the spatial size confinement of the actual semiconductor material. So within these types of semiconductors, there's a number of different interesting processes that we want to study. So because we're interested in the electrical output of photovoltaics, we're interested in the recombination of charge in light-emitting devices. We're interested in how the various types of electrical charges move throughout a semiconductor material, and what can affect them to drive them towards one process or another. So you see two images here on the screen. The one on the left shows a number of different types of transitions that can occur, very similar to a standard Jablonski diagram. So you have some type of absorption, which is the blue line for excitation. You can have non-radiative relaxation or some type of internal conversion. You can have fluorescence, the green line. You can have intersystem crossing, and you can have phosphorescence. And so those are more of the basic types of electronic transitions. And some of the other interesting things that we want to take a look at are processes that can enhance the probability of a device or a material to collect or generate a charge more efficiently. And so some of these processes can be a type of like reverse Auger process, or multiple X10 generation, where you can have one high energy excitation, a quick relaxation to convert a second electron from the valence band to the conduction band. But there are competing processes with this, such as non-radiative cooling or radiative cooling, and also hot extraction of a charge carrier. So these are different things that have been discussed for semiconductor materials, but what is it about quantum confinement that we find unique? Why is it that we want to take a look at these? And so this is just a small diagram for what happens to electronic structure as you move from a large scale material to, say, a thin film all the way down to some type of small molecule. And so what you're going to get is an expansion or separation of the discrete energy states, moving away from band structure more to just these isolated orbitals or electronic states, which increases the band gap, which is going to change relative energies for different processes as they relax or recombine or extracted out of a device. Okay. Do you have any questions so far?
What's up with the tree?
So the image up there is actually, I pasted it backwards. So you can see there's a small molecule, and then there's an excitation. And so you're going from something really small to a little leaf, like a little stem, to a leaf, to a branch with leaves, to a big bunch of branches. So it's kind of like a growing process. So, you know, solar energy, there's the sun up there, and going from small to big. I mean, I can take it out if you don't like it, but it brightens it up a little bit.
No, I just was wondering what you were trying to do with it. But
well, if it's not clear, I can take it out and just use these other two. I mean, part of it is, right, that I guess I'm not talking so much about. I mean, we're trying to mimic what photosynthesis does artificially, because that's one of the most efficient processes available. And so that's part of where that comes from, but I can easily take that out. Okay, so here, I guess what my plan to do is I'm going to introduce briefly some of the ground state electronics, heating and molecular dynamics methodology before going into the section on the silicon nanocrystals, where we're just looking at the heating and dynamics and the absorption and emission before going to the more advanced dynamics later. Okay, so with the way that we're going to approach looking at these materials is computationally. So we don't have a lab setup. It's a little bit cheaper. It can be brought into a wide range of materials. It gives us an opportunity to look at unique features that are very sometimes difficult to see experimentally. And so primarily we'll be working with density functional theory as implemented in VASP. And so starting with some type of model that we've built, we want to work to optimize the structure and find the lowest energy orientation of the atomic positions. And so when we find this type of lowest optimized geometry, what we're able to do then is to solve the Kohn-Sham equations to provide a total energy for the system, Kohn-Sham orbitals, which are going to be the basis for the furthering methodology, and also the energies of these systems. And so it gives us an opportunity to look at where densities are located on the atomic centers, or if they're found in different regions of space, and also the relative energies for different types of electronic processes. So,
John?
Yep.
Please make a note about other methods.
Okay.
You're not the only theorist in South Dakota, and Bess and Pierre may pick and ask about why not multi-reference methods. Although it is evident question, but you need to show something.
Okay. And so from these initial optimized calculations, one of the ways that we can try to look at and analyze the electronic structure is through the density of the electronic states. And so here we're looking at where on a relative energy scale are the states that can be occupied by an electron in the system. And so the image on the bottom left shows a density of states for a structure where you have on the left a filled red valence band where the states are occupied, and on the right you have the unfilled conduction band, unoccupied orbitals. And so this type of figure can give you an idea of, one, the band gap, so just looking at the band edges, so what type of energy would be required for minimum transition, but also if you would excite to one part of the structure or another, a possible effect on relaxation times. So another important tool that we have is to use an absorption spectra of a calculated model. Experimentally, UV-Vis, any type of spectroscopy has been around for a long time, and so these are reliable and tested results that we can use to compare our calculated model with experimentally measured results. And so in order to calculate this type of absorption, we're interested in where the electron density is localized given two specific states. And so Dij, our transition dipole moment, is looking at the transition dipole between two specific states of a system. And so this transition dipole moment is used to calculate an oscillator strength, Fij, which is then used as a weighting element for a specific transition within the system. And so this is all well and good. We now have an idea of what the electronic structure can look like when we're just in a 0 Kelvin, no temperature, just completely frozen system. But we know that's not also realistic. And so you need to move beyond static atomic positions and move towards something that resembles an ambient environment. And so we run heating and molecular dynamic calculations in order to obtain thermal motions of a material to try and replicate the actual nuclear motion that might be seen experimentally. So when people are taking measurements, they're not looking at just isolated static molecules. They're looking at a short time collection of information that requires some nod towards accounting for the nuclear motion. And so the heating is solved or driven by the left-hand equation. It should look fairly familiar based on looking at the mass. So if you think of the equation on the right, so force is equal to mass times acceleration, we're interested in the distribution of the energy given between the number of molecules and the relative temperature that we want within the system. So to stop there and apply the methodology that I've briefly described, we did a collaboration with a few people, Dr. Hobby and Sam Brown up at NDSU, and looking at the effect of thermal motion on photoluminescence intensity and peak width. And so here,
John,
yes.
Audience will be aware of basic general concepts and why don't you populate? I'm just waiting which slide I'm going to show.
Oh, I was trying to see see what you're saying.
Oh, okay. So why don't you try to populate quantized levels of nuclear vibrations for thermal broadening? Why do you keep nuclear degrees of freedom in classical limit? Just, you don't need to answer right now, although it is, you may just mark it and wrap it up around this question.
There. I'm going to grab a notebook real quick.
No, because it is not possible to
Isn't-
do anything else.
Isn't that what Android does?
Huh?
Isn't that what it does for its phone?
No,
Oh,
no one can quantize nuclear degrees of freedom because there are too many of them.
oh,
You
okay.
can quantize one or maybe two, but not 300. But if I never did computations, it would be a natural question. Like textbooks in physical chemistry tell about thermal broadening and substructure of nuclear and rotational degrees of freedom, why, and populating them by Boltzmann. And here we are turning to 19th or even 18th century with classical vibrations.
Okay. All right. So then going forward, how are we going to apply this? So like I said, so they were experimental looking at these different sized silicon nanocrystals, and were curious about some results they had seen in temperature effects on the photoluminescence of the materials themselves. And so what we did was we took a look at three different sized silicon nanocrystals ranging from 1 to 2 nanometers in diameter. And so you can see on the bottom the density of states for the three structures, primarily highlighting the effect of enlarged diameter and spatial confinement on the electronic structure. So going from smallest to largest, you can see a reduction in the band gap energy in a more dense grouping of states. So running heating and dynamic calculations, we're able to follow atomic positions along a given trajectory. And so what are seen here are 6 images, 2 for each model in the middle, where it's a superposition of all the atomic positions during that trajectory, showing the increased motion of the atoms at a higher energy or a higher temperature, which is what we would expect for the systems, and also the specific cone-shell orbital energy levels on the bottom figure. So each horizontal line represents one cone-shell orbital, and so you're going to be able to see the energy fluctuations of each orbital as a dependence of the atomic motion due to the temperature. And so given the change from low to high temperature, you should be able to see more of a messy type looking fluctuation plot with increased amplitudes of fluctuation for the high temperature systems.
John,
Yes.
why you stay with molecular dynamics instead of analysis of vibrational frequencies?
Why do I stay dynamics instead of vibration? Well, I mean, we're interested in the actual effects of the moving nuclei and its end result on the individual absorbance calculations.
But if you have normal mode analysis and list of vibrational frequencies, you can just add each of the frequency to the energy of electronic state and have the broadening, and also include there the change of amplitude. Do not answer right now. Plan on thinking and expecting questions from audience.
Okay. And so looking at the different temperature effects on the motion of the atoms and how that's going to change the photoluminescence for the systems, you can see the emission plots in the middle of the screen. And so going from left to right, you can see for the smallest system, we would expect to have the highest emission energy because it would have the largest band gap. And so the solid lines are for low temperature and the dashed lines are for the high temperature. So the unique feature in all three systems is that with an increase in temperature, there is a decreased photoluminescence intensity as well as an expected redshift, and also a slight broadening of the photoluminescence peak. And so in looking at the different systems, we were interested in, okay, given the number of silicon atoms in each of these nanocrystals, we know there are going to be variations in how many are on the surface, how many are, coordinated to anywhere from 2 to 3 to 4 other silicon atoms, and that's going to restrict the nuclear motion within the material. And so the left image, you can see there are 3 atoms that are circled. The one in blue is coordinated to 2 silicon. The red is coordinated to 3, and this green one here is in the center, more core type silicon, coordinated to 4 other silicon. And so given the relative percentages of silicon atoms on the surface, we're able to try to look at these trends in the changes in the photoluminescence. And so this picture on the very right goes with the table on the bottom right, at looking at this change in photoluminescence relative to the intensity as a function of the surface atoms relative to the number of total atoms fit to a given parameter. And so with this intensity reduction, you can see is much higher for the smallest system, which would have the highest percentage of surface atoms. Okay. Any other questions here?
Why there are 2 lines?
2 lines where?
On the right panel image, green and blue dash.
One is dotted, one is dashed. Okay. That is a good question. I'm trying to.
Is it like one theory, one experiment, and they coincide so good?
No, that's not it. I don't think. That is a good question. I will have to take a look.
Like 77K and one 300K?
That is probably exactly the right answer.
It says in the top right, 77, 300.
Yeah, so those are relative, intensities, but I would agree that that would be the answer. Okay. So moving beyond just our standard molecular dynamics and its direct effect on absorption spectra, we're also interested in other types of electronic relaxation processes, such as non-radiative relaxation within a material. And so what that is going to require is looking at what happens when an electron is excited, and how can we understand this electronic motion in regards to the nuclear motion of the system. And so the way we approach this is during our dynamic calculations, I showed you earlier the Kohn-Sham orbital energy fluctuation plot. So a wave function is calculated for each atomic position. And what we're able to do is calculate non-adiabatic couplings, which is taking a look at the difference or the overlap between the wave function at one time step and another. And so this middle image just shows the calculation of the energy and the wave function as a gray wall. So at each time step, there's a new calculation, and then doing a comparison between the two is going to provide us with information on electronic transition probability through time. And so given the coupling calculations, we have our 9-adiabatic couplings, and what we're able to do is try to take them and turn them into components of a Redfield tensor to predict the transition probability. And so we take an autocorrelation of these 9-adiabatic couplings, and then a Fourier transform of that. And so that's going to provide the two components for the two halves of the matrix that make up the Redfield tensor. And so this Redfield tensor is going to allow us the ability to then plug this in and look at how the density matrix is going to evolve in time. And so,
John,
yes.
which order of time-dependent perturbation theory you are using here?
Which order of time-dependent perturbation theory?
I'm asking on behalf of Aaron because he wanted to ask this.
I believe, is it second?
Yep, good.
Okay. Okay. And so, I mean, yeah, I guess we talked a lot about this last week too. Taking diagonalization of these two super operators on the density matrix is going to provide us with eigenvectors and eigen values for the system. And so primarily what we're wanting to solve is the expansion coefficients for the propagation of this density matrix, and we're able to set this up according to initial conditions within the system for homogeneity, and looking at unique initial conditions for specific transitions. And so being able to take the results from this, we can plug them into the non-irradiative relaxation dynamics, and also time integrated emission, which is going to provide different information than the previously mentioned dynamic photoluminescence.
John?
Yes.
What is surface hopping and why you don't use it?
Okay. Well, so surface hopping is a method that requires as long a time scale as you want to explore in terms of your dynamics. You'll need to calculate out that many time steps, along with possibly multiple trajectories, giving it a larger computational cost. Whereas here, we're able to look at propagated dynamics over the span of any range or number of dynamic trajectory steps, but then propagate them out to long lifetimes, or lifetimes that wouldn't be normally feasible due to computational constraints, or just if you would die of old age waiting for a job to finish.
Okay.
And so for every transition that we're interested in, we're able to set these initial conditions as shown here in the top left. And so we have an occupation moving from one state to another, and then propagating the dynamics from these initial states. And so given the energy expectation values of a charge carrier at each instance of time, we're able to look at a normalized value for this, and then fit a single exponential to find a rate of energy dissipation for that given excitation. And so looking at variations in how electrons and holes can migrate differently at different speeds through the material can give an idea of different types of charge carrier separation lifetimes of a material that might be beneficial for further application. And so, I mean, everything I showed here, I don't have any of the spin polarized equations in, but they'll be put in before the final version. Maybe more, I don't know if more just in the ground state because the propagation is going to be the same just for alpha and beta, but that'll be in here too. And so one of the other applications is looking at a time integrated emission spectra. And so what we're doing here is looking at absorption or emission as defined earlier, but now we're actually taking into account where the charge carriers are specifically populated and the energies between the two charge carriers at that instant of time. And so here we're looking at emission integrated over a whole dynamic trajectory for a specific initial excitation, and looking at the summation of possible emission during that time. Okay, so I don't know. Okay. Here is where I might spend most of the time. So we've been working currently on trying to appease reviewers for this project. And so the primary goal of this project is to take a look at what happens when you remove one lead atom from a bulk perovskite material, and what effects does this have on the electronic and optoelectronic properties within. And so here, there's a number of different things on the slide. So the first thing I want to draw your attention to are the two snapshots of the model itself. So you can see a two-dimensional slice with a red dotted ring for where a lead used to be, but the vacancy now sits. And then a three-dimensional model of the material where, I don't know if you can see my mouse, but the lead vacancy sits right in the middle. And so perovskites have a very unique electronic structure that can be somewhat challenging to model computationally. And so when we remove a lead atom from the material, we're not only just taking out, the potential from that atom, but also the electrons that are contributed to the system by that atom. And so with lead being a 2+, excuse me, a 2+ cation, what we need to do is work on restoring the charge balance by adding 2 additional electrons to even out the electrical system. So what I have here on the screen are the 3 closed shell systems. So when we're going from a 2+ with the lead removed to a neutral charge with the 2 added electrons, there are steps in between, given that we can add 1 additional electron. So we're going to end up with some type of spin polarized state, but we could also have it where when we add 2 electrons, they can be in a triplet configuration with both of them being unpaired. And so first we're going to take a look at just the closed shell systems. And so on the very top are the density states for these 3. So we have the pure, perfect methylammonium lead iodide. We have the vacancy removed, or the lead removed system. And then we have the 2 electron corrected singlet state system. So you can see that for the 3 systems, there's obviously a shift in how the energies are distributed near the band edges, but more importantly, with just the removal of this lead atom, we see the introduction of a vacancy state. And so we're interested in this vacancy state and the possible effect it can have on relaxation pathways, and then the resulting optoelectronic properties of the material. So given that, I think I have it in a couple slides, given that perovskite materials come in different geometries, leads them to have various band structures from one to another. And so here we're looking at a 3x3x3 supercell of cubic phase perovskite. And so given that we're calculating this as this type of supercell, you can see that the band gaps for the pure perfect system is somewhere close to 2.5. And so generally, these materials have a band gap of 1.6 to 1.7. So we know that there's something that was slightly shifted within the material. So one of the things that we've done is gone back and look at the effect of the multiple K points within a calculation, how that can shift the density of states within the structure. And so the middle set of images, so there's two density of states. The blue or purplish looking ones are the density of states at the gamma point, which would be close to that seen above in the top line. But then the red shaded are for the density of states calculated with a K-point mesh. And so you can see that there's a narrowing of the band gap for these materials. And so now instead of 2.4, 2.5 in the perfect material, we see a band gap of close to 1.5, which is right on par with what we would expect to see. One of the unique things is that not only is there kind of a shift of these band edges, but there's also still this vacancy state that's left inside the band gap. And so we're going to be interested in how that propagates as well through looking at some of these other systems. And then looking at the comparison between the clean system and the charge corrected system, you can see that the edges of the band are moved even more so into the material. And so the additional electrons within the system are slightly pushing the top of that conduction band down, or shifting the energy so that there's available states a little bit lower in energy. And then for the bottom are the absorption spectra calculated at the gamma point. And so normally in experimental work, we would expect to see an absorption onset somewhere around 800 to 900, given the specific halide involved in the material. But we do see, again, in the lead vacancy system that we have a small redshifted absorption peak due to the smaller or lower energy transitions from the valence band to that vacancy state. And so one of the things that I had mentioned was the dependence of the structure on, the band structure on the size of the simulation cell that we use. So we use this 3x3x3 supercell, and so you can see the band structure for the perfect, the lead vacancy, and then the charge corrected on the left. And so you can see that the direct band gap for the system is found at the R point, and this matches with other calculations that have been done. And the unique feature is that this vacancy does maintain its energy with a small change around the gamma point, but still more or less consistent all the way across the band structure. And then for the charge corrected system, you can see that there's more of a drastic change in structure in the valence band than there is in the conduction band, with a flattening of the bands and getting a separation, almost looking like there's no dispersion at specific points themselves. And then doing a comparison with an older model that we had, so a 2x2x2 supercell of the same material, you can see that now going from an odd number to an even number type calculation, you actually fold the band structure back to the gamma point. So choice of structures is fairly important in these calculations. So when I showed the absorption spectra earlier, the onsets were at an energy much higher than what we had anticipated or what people see experimentally. And so in doing these types of K-point mesh calculations, we've worked to run absorption calculations for, or at each of the specific K-points within the calculation. So what I have here on the screen, on the very two left images are the partial contributions to total absorption at each K point within the system. And so you can see that for each of these systems, both the charge corrected and the just lead vacancy, that the absorption onset between 800 and 900 nanometers is primarily contributed by one K point. So by only taking absorption at the gamma point in our last set of absorption spectra, misses this onset peak, which is one of the nice characteristics of the material, having a low energy absorption. And so then this middle B figure is just a look at the partial contributions versus summing up the total of all of the spectrum. And then on the very right, the most intense peaks are again the sum of the absorption intensity from all K points, but then the dotted lines themselves are just the average. So taking the total sum and dividing it by the number of K points used within the material. And so I checked this with, well, for those who use our codes, you can generate the oscillator strength files and then take these oscillator strength files and turn them into the spectra that we put into figures. And so one of the ways you can do that is, one, you can either take the spectra files, just add up the totals and divide to find the average like I did, or you can take all the oscillator strengths and combine them into one file and regenerate just a new singular spectrum. And so this bottom C panel, there's red and blue. And the red is the average, and the blue, it's labeled HPC. So there's not a huge distinction between the two values and just averaging them, on Excel, or actually rerunning a distribution of the energies using the spectrum.
What is HPC? Sorry.
So that was just I concatenated all the oscillator strength files from the K points into one oscillator strength file, and then ran like the spectrum code to generate the spectrum file.
Okay, but HPC, what does it stand for? Is it an abbreviation of something?
Well, that was just a moniker for me, that I calculated it on HPC instead of just in Excel, like our HPC, high performance computing.
Okay, so it doesn't deal with way you compute the spectra.
No, just where I computed the spectra.
Okay.
Just personal identification for me. So obviously it's important that we're going to have to take a look into the effect of K points. Well, not only on absorption, but then you also have to assume that based on these values, it could easily play a role in the opposite process of emission. But one of the other things we wanted to take a look at was, so we know going from an odd to an even numbered supercell shifts where the direct band gap is, and the fact that we're calculating at the gamma point. If we go larger, what also happens? And so here on the right, I'm showing the absorption spectra for two supercells, a 4x4x4 in red and a 5x5x5 in black. And so you can see in the black, the band gap is again, well, it's shifted slightly below 2.5, so it's probably close to 2.25, 2.3 at that first peak. So noticeably shifted, getting closer, whereas the 4x4x4 is again 1.6 right at the expected experimental value. So we know going to an even numbered shifts where the band gap is, but more importantly, going to this 5x5x5, so increasing the size of the total unit cell is shifting the band gap closer towards the experiment, or shifting it towards the gamma point, which is what we would want to see.
Which experiment? You told closer to experiment.
So, well, experimental band gap values are 1.6 to 1.7 electron volts. And so one of the arguments we had made was in regards to, you know, in an infinite cell, you would have everything expected to collapse to a band gap. And so I think we're seeing the effects of, you know, going from 3x3x3 to 5x5x5. We're having a shift of, you know, almost, well, exact onset, I don't know, maybe close to almost half, you know, maybe not, maybe a quarter of an electron volt. And so there's some size dependence on actually seeing it push back that way. So I don't know how big of a unit cell we would actually have to get to have it be pushed all the way back to the gamma point. But that was kind of the point I was trying to make.
Okay.
And so, so those were for the closed shell with no spin polarized calculations. And so we also have two other systems with one additional electron added for a charge system, but then also the two electrons forced into a triplet type formation. And so on the left, top left, there's two density of states plots for the one electron charge system. And so you can see that in the left plot, just solely found at the gamma point, there's an imbalance with more electrons in the spin up or alpha configuration and an unoccupied beta orbital very, very close to the valence band edge. And so in comparing it to the electronic structure calculated with a K-point mesh, we can see that there isn't a huge modification to the structure itself. There's a little bit of a retraction of the alpha electrons at the valence band edge moving back in. And you can see that unoccupied beta state is sliding closer to the top of the conduction band itself. And so the absorption spectra for the ground state gamma point material is found on the bottom left. So the black is the total absorption, and the dotted red and blue are for the alpha and beta contributions to the absorption itself. And so you can see the primary contributions above 800 nanometers are going to be from the beta portion of the system, where you have that small excitation energy moving from the top of the valence band to this unoccupied beta state. In looking at the triplet state, so we can look and compare the triplet found just at the gamma point and the charge just at the gamma point. And you can see that they're very, very similar in structure, with the exception that there's now additional electrons in the alpha configuration of the triplet state. But there's a more drastic change when adding a K-point mesh to this type of system. So instead of just having this beta unoccupied state shift a little bit closer to the top of the valence band, you now almost have it completely emerged into the valence band itself, and have a stretching of the, well, a more even distribution of the states in the conduction band. So this type of shifting in the conduction band is going to affect relaxation of excited electrons within the material. And so the absorption spectra for these two, again, the black is the total on the top right here, and then the dotted lines are for alpha and beta, where you can see that the beta again provides a redshifted peak, but then once you get past about 1500 nanometers, the alpha component begins to take over, and it actually skyrockets and balloons up to a really high intensity of the material. And so I think part of this is due to the fact that now that you have this type of additional electron population in the alpha configuration up into the conduction band, you're going to have lower energy transitions available from one to another within this now densely packed state or range of states within the material. So one of the other important things which I need to add some equations on is the effect or known effect of spin-orbit coupling within perovskite materials. So given that there's big heavy elements like lead in them, relativistic effects like spin-orbit coupling, how the electron is interacting with the heavy nucleus itself, can affect the energies of states available for population in the system. And so on the left are four absorption plots provided by Dr. Interbev, one of our collaborators, as kind of our first attempt at trying to account for spin-orbit coupling within the ground state structure of these materials. And so, excuse me. The plots themselves are for, the top left is for the pure material. And so you can obviously see with the spin-orbit coupling added or moving away from a really high absorption intensity at 2.5 and above and shifting it back down to somewhere close to 1.6 as would be expected. But there's also a unique feature below that, which I'm not 100% sure if that's just a little bit of noise in the calculation itself, or if it's taking into account intraband excitations that are included in the oscillator string. And so through all four of the different models, we're seeing this lowering of initial excitation energy, and comparing it to other types of computational experiment. One of the main things that happens is you're having this splitting of degenerate states at the bottom of the conduction band, and you have a broadening of the density of states of the conduction band coming down into the band gap of the material if there wasn't spin orbit corrections. And so on the right, I have a density of state plot, which I don't know if this will make the final cut, but this is just trying to show an example of the density of states for two systems with and without spin orbit coupling corrections added to the DFT. So the solid lines in the figure are for spin orbit coupling corrections, and the dotted lines show density of states for just the pure DFT that we had calculated. And so the black and the red dotted lines correspond to the pure material. And so you can see the biggest shift in energy is up in the conduction band of the material. And then the blue line and the green dotted line correspond to just the lead vacancy material itself. And so one of the interesting things here as well is not only the reduction of the band gap energies, but also the maintenance, or the fact that the vacancy state is maintained within the band gap even with the spin orbit coupling correction. And so this is kind of still developing. So this is where the spin orbit coupling corrections will end for the calculations, but we're working to try to include them into the results. So everything here up to this point was all still ground state. Calculations, and so moving forward, part of what we had introduced was the dynamics of the charge carriers within the material, and so we're interested in how these charge carriers can move in the perovskite materials. One of the unique features of these perovskites is that upon photoexcitation, you can actually have an exciton turn into two separate charge carriers within the material itself, just because of the unique properties of the material. And so in running the dynamics for the multiple systems, what I'm showing here are the cone-shell orbital energy fluctuations for each of the specific non-perfect systems. So on the left is just the vacancy system. The two images, second from the left, are for the charge system, and then we have the singlet version of the charge corrected system and the triplet versions or trajectories for the triplet system. And so one of the things that we were taking a closer look at was in the very left in the lead vacancy system, you can see that there's a unique feature in the middle of the band gap, just above -5, that you have a huge fluctuation in the LUMO +1 orbital, and also a very large fluctuation within the LUMO orbital as well, that's almost seated on top of the conduction band. So you have the loss of this middle energy state going up into the conduction band, but then you have a detachment of a state away from the valence band going up into the middle of the band gap. And so that's something that isn't necessarily seen in the rest of the systems and could be a very unique feature moving forward. So
John,
yep.
I ask here. So please comment. I do not know how to formulate question, but it just induces curiosity.
Mm-hmm.
So this large or huge amplitude fluctuations may witness two things. First, that the prior to thermal motion, the model was not optimized, and then it is a question to like, is it a good data? Should one optimize for another 10,000 hours before going to dynamics? Second, that maybe for ideally optimized system, there are isomers that are activated by heat. So when you are heating and running for molecular dynamics, it is not equilibrium dynamics around the equilibrium point. It is highly non-harmonic. The system experiences reaction, exploring transition state with some activation energy, and maybe by the time you are done showing this 1000 femtoseconds, the reaction hasn't been complete. System didn't came to another equilibrium point. What is your vision and interpretation on these aspects?
So, well, I mean, I was going to kind of try to allude to it later. I would agree more with your second statement. I mean, I think that, well, so we know with the different phases of geometric configuration for these materials, the cubic phase that we're using here is the highest temperature known system. So you're looking at above like 3 what is it, 320, 340 Kelvin. And even then, it's almost kind of in a pseudo-cubic type phase, whereas it's going to change to a tetragonal phase at room temperature. And so if we would indeed build this cubic supercell of the material and allow it to optimize, since optimization happens at a low temperature or 0 Kelvin, we would expect to see a restructuring of the material and trying to form back into, even all the way back down to the orthogonal phase. And so I think part of the fact that during heating, I mean, we have this rescaling of velocities going up and down and trying to get to some environmental value. We could have some effects of geometric reshaping, since it's not always at the exact temperature. But from the dynamics and looking at new molecular formation during the dynamic trajectory, I would think that if we would run this, say for another picosecond, I would think with the formation of an iodine molecule itself, I would think that we're going to see a stabilization of an energy within the band gap for a long period of time until that iodine either gets close to another lead atom and you have formation of some new chain, or you have some type of ion migration passing through a wall of the material. So I would expect that we're towards the end of this trajectory, we're reaching some type of close transition point, like you had mentioned, in the formation of this new molecule that could be, either short or long-lived, providing, something that is a unique environment within the material itself that could have, unique characteristics or shoulders within emission spectra.
Okay. Do you have dynamics running for another couple of femtoseconds, picoseconds ongoing?
Yes, it's going slow.
Very good.
But
very
there
good.
should
Even
be
if
some.
you are not doing it, it is healthy to tell that I'm trying to.
Yeah.
Okay, please keep going.
Okay. And so, I guess this is a question. So some of you heard the talk that I gave in Fargo, and I went more into detail on where the actual charge carriers, the partial charge densities, and the dynamics, like the RDF values of iodine, form in that specific trajectory. I don't know if that's worth, more time, as it's, something that may or may not be beneficial. That's something to think about. You can mention at the end. Okay, so in looking at these, I don't have them all up here. Looking at the transition probabilities that are calculated and put into the Redfield tensor from the non-adiabatic couplings, what we're able to do is look at the amplitude of these values and know where or potentially at what speed we could expect to see a transition happen from one state to another. And so they're on the diagonal because we're expecting that transitions of lowest energy, so anything one off the diagonal, are adjacent states are going to have the highest values for transition. So looking at the perfect to neutral, and then looking at just the charge system, you can see that for the perfect to neutral, the intensity of transitions are generally higher than those for the charge system itself. But one unique feature is that holes are always have a higher probability of transition coming back up towards the top of the valence band compared to the electrons that are excited up in the conduction band. This is also seen, thinking back to the density of states figures, just looking at the sheer volume of states available at the valence band edge compared to the conduction band edge. And so here, what I'm showing are 4 examples of specific initial conditions for measuring rates of electronic relaxation. And so here, what I've done is choose transitions according to their oscillator strength. So looking at the most, one of the most probable transitions for each of these 4 systems, there's an initial excitation happening at the left. And so the red represents gain in electronic population, blue represents loss of electronic population, and green is equilibrium. And so you can see for these systems, one that just like the Redfield images, you can see that the hole relaxes faster than the electron, so tau h, lifetime of the hole, and tau e, the lifetime of the electron of the system. So one of the interesting things about these images is that it gives us an easy visualization of how long these charge carriers can exist and at some type of given energy. So say take the neutral or the charge down system, you can see that there's a higher, the electron itself doesn't lose a lot of energy even before 100 picoseconds, giving it the possibility that charge collection of this hot carrier could increase the photovoltage of the material. And so the perfect and the charged up, because they have similar density of state structure with no vacancy state, also have similar dynamics, whereas the neutral and the charged down system, given that they have in an inner band gap state, are going to have similar lifetimes of electrons within the material.
Aaron, can you ask John about double exponential, multi-exponential feed?
Was there one in there?
No? So I asked why it is not there, or launch the discussion.
Or what? Oh, like in the charge down.
Well, formulate question as you understand it, because otherwise it will be biased to my train of thought.
Yeah, I guess why isn't it double fit?
Okay.
So
so
reformulate question of Aaron now.
No, but did he fit? Isn't the dash line just the ensemble average? Or is it a fitted line?
So the dash line is a single exponential fit to the average expectation energy of the charge.
Oh.
And so, well, one, to answer the question head on, I'm working on calculating a double exponential or multi-exponential fit for some of these systems. Hence our discussion the other day. So one question I have, or one thought I guess I have on fitting multiple exponentials to these charge relaxations. So we can look at, okay, so say we have a trap state like this interstitial unoccupied state. If we know that this vacancy state is more or less a bottleneck, we know there's going to be a consistent relaxation time from this vacancy trap state to wherever else it needs to go, or from somewhere up in the conduction band down to this vacancy state that is the lowest unoccupied state. So we could have some type of constant time scale for relaxation from one to another, such as the LUMO +1 to LUMO, or if it would be in the valence band, a HOMO -1 to HOMO. And so my thought on this is we can do those calculations and and do the subtraction of the time scales like we talked about. But I guess one question I have is, if we're just subtracting, one specific time from of Lumo +1 to Lumo away from Lumo +3 to Lumo, can't we do it where we actually change the value of the HOMO level in the initial excitation script and populate one more state so that it's more or less a true relaxation from Lumo +3 to Lumo +1, or does it not make a difference?
You can do several tricks. For example, you can disable transition from Lumo +1 to Lumo, and then use old formula, and then populate Lumo +1 and explore transition to Lumo and get a second exponential. Or you can just add a line of a code that will do it double exponential. Those of audience who has a classical education in chemistry may have taken course on kinetics.
Yeah.
And you should be aware how the rates and times of processes are added or subtracted when there are subsequent processes.
Yeah.
So there should be some standard rules. So please launch discussion. John, if I've told something strange, ask Levi because he expressed enthusiasm, and Brandon, if it is known for you, do not ask them. Or Brandon and Levi, if you want to, you may.
But,
John, not to me.
So I guess when I've looked through papers on non-adiabatic dynamics and non-adiabatic excited molecular dynamics, they typically look at the population, not energy. Because in that case, then what you can do is you can monitor the population of the, like a band of states, and typically you see a quasi-exponential decay, and then your intermediate bands you see increase, and then you have a time where you have I forget the technical term, but it's virtually zero, and then it jumps up. And I know Sergey has papers on this, but I don't remember what it is now. But I think we've talked about this, and you're like, yeah, we don't do that way.
I'm trying to remember that conversation.
Because in that paper they did a single exponential decay that's irreversible, and they modeled it as going from like A to B, B to C, and then you get a formula that is all single exponential, but then they greatly influence your final formula other than just a single exponential.
Well, I mean, I know, like, even in in calculating photoluminescent lifetimes, I mean, when there's multiple processes that can occur, and Yulun would be more experienced at this, but you can have multiple exponentials that are summarized together in terms to get the total of the rate or the lifetime for the system. I have to go back and do a little bit of reading.
I'll try and find you the paper I was talking about and send you the link.
Okay.
Thank you. I have another question. Provocative. You know it is open problem. So, electronic relaxation. How much the data that you are showing would change in presence of K-point dispersion and spin-orbit coupling? In previous section, you did show how absorption and band structure change So how much even if the data are not available, do you have intuition if this spin polarized data can at least guide the intuitive interpretation of qualitative processes in the material?
Okay, so with so I guess I'll ask a question first. So when considering relaxation from one K point to another, is it generally slower? It would slow it down, or would it speed it up?
Do you ask about vertical transitions with momentum conservation or diagonal transitions when a phonon removes part of the momentum from electron?
So I guess in my mind, I'm thinking about horizontal transitions, because you would need additional vibrations to try to account for any types of energy lost during transition from one to another. So I mean, I would think it's slower, but I'm curious on your thoughts.
Intuitively, momentum dispersion should speed up relaxation, because the resonance matching of the electronic and nuclear frequencies should be met more often. So whatever data are obtained for 1K point with momentum dispersion, it is expected to be quicker.
Okay. And so then with the addition of spin orbit coupling into the system, because it's creating states that are more, they have larger spacing towards the edges of the conduction band. I mean, with that alone, we generally would assume that relaxation will slow with increased energy between states near band edges.
Okay, it's a good idea. I do not know if it is right or wrong, but it sounds reasonable.
And I'm
on one hand, but on another one, their Spinorbit would enable some transitions which were spin
previously
forbidden.
unavailable. Yeah.
Yep.
Okay.
If the data will be not ready by the defense, you may just express concern and make extrapolation.
So, so is Dr. Innerbev running the calculations for the spin orbit coupling or spin orbit coupling files?
I'm not sure.
Okay. Well. Okay. So then, I guess, so one of the other, where are we at, 5:30? Oh boy. Okay. So one of the things that I mentioned earlier that we use, or we can get from dynamic calculations, is a time integrated photoluminescence. And so we're interested in the rates and how these charges are moving, like I showed in these green figures, and how the specific populations and energy differences coupled with the oscillator strength values for those transitions can allow emission to occur. And so here, what I'm showing are radiative emissions along a trajectory for the vacancy and then the spin up and spin down charge systems, with the other systems being produced right now. And so one of the main features that you see in this type of calculation is a very large emission peak, one at the band gap in the material. Because we don't allow recombination of the electron and hole once they're finished migrating to the band edges, the emission can be long-lived. But we also see a large range of emission values occurring at values lower than the band gap, where these would be, possibly infrared materials if the materials actually did emit or at NIR values, but they're mostly just subsequent due to intraband transitions at low energies. But the unique things that we were interested in occur above the band gap energy. And so when we're looking at peaks above 2.5, we're seeing high energy emission coming from specific initial conditions. And so when we get these types of emission events, it's possible that we can show that for a specific environment in the material, we could get this type of bright emission that could be used in lasing or other optoelectronic properties within the material. And so being able to calculate the non-radiative rates that we have and also the radiative rates, we're able to calculate quantum yields for the material. And so here in the neutral and spin down systems, which if you remember the density of states are similar because they both have a vacancy state, the quantum yield is very, very low. Whereas with the spin up state, it's much closer to that of just the perfect material. We have a higher quantum yield, somewhere close to 50% within the material. And so this, I need to bring up with the triplet data that's running right now, because I sent Aaron a paper the other day on bright triplet emission within cesium lead iodide or multiple halide materials, but also could be a possible indication that it's also a possible emission event in the methyl ammonium as well. So in comparing the non-radiative rates for all of the systems, so with the pure system here in the top left, you can see the electrons in red, holes in blue. The electrons are faster than the holes, which is what we would expect. For the pure system, you can see that they're set in almost identical pairs of two, where looking at the density of states within the material, they're actually sets of degenerate states. And so the rates are just slightly different at variations in energy of the material. And then looking at the vacancy and charge corrected state, you can see that there's a unique feature for the electrons that is very, very slow for relaxation time due to the larger energy that has to be overcome going from the LUMO +1 to the LUMO to that vacancy state. And then looking at the charge corrected state, you can see again that the electrons speed up again somewhere in the range from 2 to 5 picoseconds for this first initial 10 states. But one of the other unique things is that the hole almost maintains a constant relaxation time for these first number of states. And so I'm trying to still figure out necessarily what the root cause of this might be. And so the fact that we were interested in the multiple K points within the system, we know that accounting for multiple K points along the molecular dynamic trajectory can affect the velocities and forces felt on the ions. We wanted to see once what would happen to the dynamics if we include these K points into new coupling calculations. And so looking at this vacancy system, we can see that there's a very unique shift in the fact that we now have electrons trending in the manner in which we would expect. So somewhere close to a linear relation between dissipated energy and relaxation time compared to that of the previous system where we had extremely slow dynamics, 60 to 100 picoseconds, and now it's shifted down 25 to 35. And then looking at the charge-corrected system where we have electrons in a similar trend as that for the just gamma point trajectory, but we look at the time scale and everything is shifted inside 1 picosecond, which is more or less what people have been measuring, looking at electron relaxation somewhere in the range of 750 femtoseconds. And so for these first number of states, we're getting really fast relaxation. And then we have a shift in the whole relaxation rates away from this homogeneous plateau to a trend similar to that of what we'd expect with a linear, almost gap law type fitting.
What is
so, gap? Okay. Gap law is looking at the rates of transitions that occur between states closer in energy are expected to be faster.
Okay.
So smaller dissipated energy, faster time. So one thing to note about these dynamic trajectories, though, and the couplings generated with it, so the molecular dynamic trajectories are calculated with the K-point mesh, but the coupling values themselves are calculated at the gamma point for the system. And so, again, we're going to get...
He doesn't see. John, can I ask something?
Yeah.
Please bring the slide back.
Which one?
The same where you were. Yes, this is fine. Let's go to the... So, do you see?
Oh, crap. Okay, so you're pointing...
So you do have this red feature?
Yep. Mm-hmm.
Which is offset by the relaxation from the trap backwards to the ground state. So all of these data points are offset vertically by the time, which is like 60 picoseconds to relax back to the ground. And if you do, answer a question by Aaron and do more like multiple exponentials, you can bring it back. But your gap law tells that time should increase as you increase the excitation energy. And here it goes opposite. Time decreases. So is it an artifact or there is an interpretation? How would you comment on this?
So we had seen this once before in looking at our quantum dot structure and having this almost reverse type relaxation event. And so in looking at where these multiple states are localized, the partial charge densities could be closer to overlapping, between states that are multiple indice numbers apart. And so you could have states localized on the lead at lumo plus 2 and sorry, lumo plus 2 and then lumo plus 10. Well, because they're so localized, the overlap between those two states allows for a very high or fast transition. more so than actually decaying through states that might be more localized on iodine or hybridized between multiple atoms. And so you could have an almost jumping type effect instead of standard thermal or standard cascade thermalization, where every state from the initially excited state down to the LUMO is involved in the relaxation. You can have jumping of states that share more common spatial localization.
Okay.
Okay. And so is the connection going to break at like 5.2 again?
If the connection will be broken, then we will continue next Tuesday.
Okay. All right. So that's a look at the closed shell dynamics of the systems. And so here I'm showing the open shell non-radiative dynamics of the systems. So we're looking at the top left two for the gamma point trajectory of the charged, and then the bottom two left are for the triplet gamma point, and then we have the MD pairs that correspond. And so again, we have some slight shifting of rates and trending between systems of spin polarization and the dynamics, the K-point mesh dynamics. So with the charged alpha, you can see the relaxation rate of electrons and holes follow almost the same slope. But moving to a dynamic trajectory, you can see that now instead of having the same slopes, the electrons almost increase in relaxation time exponentially as multiple states are bunched around the same type of energy dissipation value. So when we were looking at the density of states, you could see more of almost like a Gaussian distribution for the gamma point, but then moving to the dynamic K-point mesh, you had an elongation and broadening of these states. And so there could be something where, because now you have the first number of states more localized, lower in energy away from the bulk set, you have this faster relaxation coming in. And then for the spin-corrected triplet calculations, we have the same thing that we were just discussing. You have whole relax, oh, just kidding. So for the triplet state emission at the gamma point, we have almost opposite type rates. So we have the holes being very, very slow for the alpha compared to the electrons, which relax very quickly, because if you remember, there's extra electron density in the top of the conduction band. And so anything that gets excited up above into the conduction band can relax very quickly to the HOMO because it lies above the conduction or band gap. But that hole is going to have to travel through the valence band, bridge the energy across the band gap to get to the HOMO value. Whereas in a vice versa type situation, the beta component of the material shows a very slow electron relaxation versus a fast hole relaxation because of the pushing, or well, because of the unoccupied beta band close to the top of the valence band. And then moving to the dynamic trajectory for the triplet system, you can see that, like we were talking about before, we have a drastic change in the dynamic rates of the material. Now, I don't have the density structure pictured here. Maybe I'll put it in, is the density states for the triplet state, the density of states for the K-point mesh, and then just the density of states for the gamma point taken out of the K-point mesh itself. And so one of the things that I've noticed is inside this K-point mesh calculation, you get an uneven distribution of electron density between K-points. So you have specific K points where instead of having one electron localized in a HOMO orbital, you're ending up with 1.5 or 1.3. And inside, say, the band gap, you have almost no discernible separation of electrons. So you get the same HOMO and HOMO value for spin up and spin down at gamma K point, whereas if you would say move over to M or X, you get where the actual electrons form into the triplet state. And so I think that's part of what's driving this set of data to have very, very fast or very comparable relaxation times between the two different charge carriers, is the fact that the calculations carried out at the gamma point instead of taking into consideration multiple K points. And so yeah, so I don't know if you guys have thoughts on that. That's just something unique that I've noticed, and I'm trying to consolidate a little bit. Okay, so we've got probably like 10 minutes left. Are there any questions up to this point before I go forward?
So I guess what's your conclusion?
On what's happening with that?
Yeah, because
Or
like,
just
well, normally I expect like you start a section and you kind of can like figure out like you conclude. Like,
okay. So
what you figured
so
out
just
throughout
in
this whole study.
so just in general, you're saying add conclusions to each section.
Mm-hmm.
Okay, that's fine. I was going to save it all for the end, but it's probably better and will help people a little bit. Okay, so so part of me is partially torn between what we found so far with knowing what we've calculated and knowing what needs to be calculated, and looking at the value of the spin polarization calculations for the material. So I think with the addition of the spin polarization, or at least in correcting the charge imbalance, even in the singlet form, I think that helps move towards an actual environment of just a single lead point defect. With the spin polarization, I mean, it's obviously very unique, just on the fact that because there can be unique triplet type events, I think it could be very helpful in looking at where is yeah. So I mean, the fact that you can get these long-lived type states in charge carrier separations allows for something that could have a high energy or possible bright event. So I don't know. There's a couple more things that I'm working on producing, some of the radiative and photoluminescence for these triplet states that I'll have a better conclusion once those are finished too. Okay. A very roundabout answer. Okay.
It sounds like you are hoping that the connection will be cut and you do not need to continue the rest of the talk.
No, I was just, if there's no more questions, then I'll keep going. That's so okay. So in looking at these bulk materials, we had rates for the perfect system, in the range of 1 to 5 picoseconds, and then dependent on different types of environments, we'd have.
Your call will be disconnected.
Bye.
We'd have, okay, bye guys.
Okay, well, many thanks for listening to John and helping him with questions. So if you were developing some feedback, please submit it to him directly as a scanning or sending you notes. I don't know if Levi was typing comments to John or just working on his own emails.
There was some work of my own.
That's fine.
Where did you find out that the application for the awards is earlier than December 31st? Because on the website it still says December 31st.
I've got a personal email from organizers.
Oh.